Welcome to Recycled EV Content, demystifying the complex world of battery recycling, breaking down the technical so you don't have to. My name's Scott, and I'm so glad you've joined us today. My guest is Zarko Maselja, Chief Technical Officer of American Manganese. Hello, Zarko. Welcome.
How's it going, Scott?
Going great. So, Zarko, can you tell us a bit about yourself and your company?
Yeah, well, like you said, CTO of American Manganese, focusing on the recyclable patented process, which is recycling and upcycling of waste lithium-ion battery materials, recovering materials like lithium, nickel, manganese, and cobalt, and upcycling that into the high-value products within the lithium-ion battery supply chain, such as cathode precursor materials and lithium chemicals, such as lithium hydroxide and lithium carbonate.
Now, you guys are working towards finalizing your lithium ion recycling demonstration plant. So, can you tell me a little bit more about this project?
Yeah, that's a really exciting milestone for our company. Starting in 2016, when we started working on the recycling project, we've come a long way from the initial concept work to the lab scale work, pilot plant work, and now finally this demonstration plant project. Taking all of that data from those years, modeling the flow sheet, getting the appropriate size equipment as well, and just putting all of this together at this scale to run continuously, and to validate that process at the next scale up. I think it's a very important step in any technology development process and project. You need to, the first question is, how does this scale? That's what anybody will always ask. It's a great technology on a lab scale, but how can you do this? Can you do this at a larger scale? And that's really where the stage we're at now. And with this demonstration plant data, as we test throughout this year, the different processing steps and diligently look at everything, making sure the efficiencies we achieved on a smaller scale to look to achieve as well on the demonstration plant scale. And then with that data, take that into commercial plant designs and move forward onto that next step. So critical point for us. Some more maybe I can add on the demonstration plant is, we announced that we started the feed of cathode scrap material through the demonstration plant. So maybe we can talk a little bit more about what this feedstock is as well. And that going through now our different stages of the demonstration plant, starting with that pre-leach stage and looking at what engineering challenges are we going to face, what do we need to adjust throughout this process as well, to as we learn at this next scale up.
Yeah. So then, with that feedstock, what have you guys been running through? Or I know you guys have, with your pilot plant, you had proved out with some different materials. Do you mind just talking kind of about those materials that you've tested out and proved out with your process?
Yeah, actually, and I mentioned the pilot plant. Maybe I'll kind of differentiate. What was the difference with the pilot plant and the demonstration plant? Pilot plant was at a small, it was a larger scale, but smaller scale and batch processing. So we tested out throughout the flow sheet. We tested out different stages, and then kind of moved that material through until we made a final product. The demonstration plant is now scaled up, and the intent is more of a continuous operation. So really running continuous material through as you would in like a real world operating conditions. And what that material input is cathode scrap. This cathode scrap is essentially when you're making a lithium ion battery or lithium ion, like the components are being put together. You have the different components of a lithium ion battery. So you have the cathode, anode, separator, and electrolyte as your main components. The working the other way, anode being the copper foil with graphite. You have the separator in between the cathode and the anode. The electrolyte is a liquid fill, and then the cathode is your aluminum foil with some kind of mixture of lithium, nickel, manganese, and cobalt, depending on what kind of chemistry. And then throughout the process of making that cathode, when you're coating the material, the active material onto an aluminum foil, there can be failure points throughout this process. that doesn't pass quality control, and then that ends up being scrapped. It's it's not a waste really, because you have a very high concentration of these very valuable materials, um, but that scrap rate can be very high at a gigafactory, especially in the early stages. And I think this is what we see as the major source for recycling in the early stage. And then this is where we've also sourced, a few metric tons of that material for processing at the demonstration plant. Now there's another potential feedstock, or future feedstock, known as black mass. This now comes from those batteries that did pass quality control, did end up going into an electric vehicle, for instance, and then it finally reaches its end of life, and then that whole pack needs to be kind of worked backwards, from the disassembly of the pack, module, cells, and shred it all into a black mass. And that also has a rich concentration of lithium, nickel, manganese, and cobalt. And this is material we've also tested on like a lab scale. But right now the focus on the demonstration plan, what we started feed of, is the cathode scrap material.
And then, so I'd like to do a bit of a deep dive kind of into the process, and kind of with what you can share without revealing any of those super secret things. But can you kind of talk about kind of what makes your guys's process special in the hydrometallurgical space? I know you guys have it's a little bit different than the traditional hydrometallurgical process, but if you could maybe talk kind of how yours differs, or what it adds to the value chain in that regard.
Sure. And sorry, I know things keep popping into my head from the previous questions as well, but I know in that there's the different cathode chemistries. I'll just quickly finish up on that.
Oh yeah, for sure.
We looked at LMO, like manganese, lithium, LCO, which you find in like your very early stage batteries, or early on, like the mobile phones. So that's a high cobalt content. So we really looked at some of those in our early research work. But now seeing the trend in the markets, and the modern chemistries like NCA and NMC, that's the primary feedstock focus right now for us as an input material. So just finishing off on that, but a deep dive into the process, and I think you'll see, in the news, hydrometallurgy being used. There's pyrometallurgy versus hydrometallurgy, but that's still a broad term. Hydrometallurgy can be divided up in many different ways in terms of the process chemicals you're using. There's and it leads to different outcomes as well, right? So I think when you look at, and this is really originating from our manganese work and how we came about our development and our technique, is work that was done primarily in the manganese side when we're working on the Artillery Peak project and that material. So with the cathode metals, they come in a high oxidation state that then requires a reducing agent to help with the dissolution of the metals. So a reducing agent with sulfuric acid to help to achieve that leaching efficiency. So what you've seen in our patents is, and what comes really from our history in the manganese work, is the use of SO2 as that reducing agent. So we see SO2 as a practical process chemical to use as a reducing agent. It's commonly used in various industrial applications, so it's not really exotic in a way, but it has an application already. And so we think about those are important things to think about when you think about scale. So yeah, it's practical, it's efficient, and we've shown complete extraction of the cathode chemistries we've tested, like LCO, NMC, NCA, and LMO, and that's with the SO2 and sulfuric acid. But then when we look at what's commonly out there as a reducing agent, is the hydrogen peroxide, which is H2O2, and relative to SO2, hydrogen peroxide catalytically decomposes in the presence of metal oxides. So you can have a very high consumption of, which I guess that would lead to much higher consumption of your other process chemicals, your other reagents. So at a small scale, maybe that's insignificant, but on a large scale, if you're using more chemicals, that leads to more costs, those higher operating costs. Hydrogen peroxide also does have very unpredictable reactions, and at a large scale, sometimes that can be hard to control. I think you can go on YouTube and search up kind of some fun videos and seeing how hydrogen peroxide reacts with different metals, and that can become a concern. And then the larger plant, maybe you don't know everything going in, and something can cause can be a risk to the operation. And then with that compared to SO2, hydrogen peroxide produces a lot of excess water that would then need to be discharged as well. So the environmental impact is from what we see worse as well.
Okay. Now, if I can ask just with that, so when we're dealing with lithium-ion recycling, the battery recycling, I should say, the metals we're dealing with, those are the oxides, and those are going to cause that, like you talked about, on a larger scale, you're going to see a larger consumption of your hydrogen peroxide and
sulfuric acid. Yeah.
And sulfuric acid, right? Rather than the SO2 as you talked about.
Yeah, so we use like an SO2 and sulfuric acid. Like SO2 helps as well, like it's that reducing agent, right? So it's really hard when we think about, with especially on patents, kind of, the change of one chemical can lead to, drastically different operation.
Right. Awesome. Okay. Thanks for explaining that.
Yeah. But and then there's more, right? That's really more.
Awesome.
Yeah. So there's more, even the leaching. So that's the leaching of the materials. But then when we look at kind of what's next, when you have it all leached in solution, right? What you see commonly out there is solvent extraction. So solvent extraction, you're adding in more chemicals like solvents that will then pull out like individually nickel, pull out cobalt, right? So you have more individual streams of these materials. But then you have to really think like, what's the big difference? Because with American Manganese, let's say we're recycling NMC, we would co-precipitate out the nickel, manganese, and cobalt together, right? And then so we have to really go back to like the history, like why is solvent extraction the one that's being used, right? And then you think back when you had the initial cell chemistries, you had LCO, it was lithium and cobalt. So logically, to recover the cobalt, you would use what's used in cobalt mining commonly, right? It's solvent extraction circuits. But now modern chemistries use an NMC, and now you have more of a mix of metals. And now you're going through this effort of individually extracting nickel, manganese, and cobalt. And if your purpose is to put them back in the battery, then that nickel, manganese, and cobalt that just got extracted individually is recombined to make your precursors and cathode active materials. So it's just these additional steps. But then also that mix of metals makes it more difficult to target, nickel or the manganese or the cobalt, right? Before, if it was just lithium and cobalt in the solution, it's easier to target the cobalt and just pull out the cobalt. So we really just see, why would you do all those steps when you can just, end up pulling out the nickel, manganese, and cobalt together? Is our logic. So we cut down on the steps. So you have minimal processing steps, right? We haven't announced our life cycle assessment results, but from the preliminary results we see compared to these conventional methods, we see that that's lower environmental impact. So we hope to have those numbers out as well. And then, and I think part of our process as well is efficient lithium recovery. We won't get into the details here, but we do have, like in our patents as well, up to the 100% lithium extraction, which is ironic with many processes. It's called a lithium-ion battery, but the focus seems to really be around the nickel and cobalt extraction, and lithium is lost, especially in the currently commercially available recycling operations, which are high heat smelting. You're essentially burning the lithium into a slag, and losing a really valuable product. So yes, the efficiency of our process. I mean, all of it really comes down together to minimal processing steps, efficient recovery of all the materials, closed loop, not and really compressing everything in, and then as well the upcycling of that material. So not creating more of an intermediate grade product that needs further refining, but upcycling, as we've shown in our press releases, where we make cathode precursor materials, which is that higher value product.
Thanks for that. I know that's a lot to digest, but I really appreciate you kind of breaking that out for us. And so, as you hit on it, the main advantage of using your patented process over the industry standard, where you see the individual battery metals broken out, is I think what you alluded to in the what you saw in your preliminary results in your life cycle assessment, just a lower environmental impact, and my assumption would be a reduced cost in terms of reagents and electrical and all the things that go into that. Is that right?
Yeah, what we see from the third party reports on the life cycle assessment, I can comment on that. On the economics, I don't really have a definitive number from what somebody would be using or what their costs are, but my intuition, at least, and I look at less steps, less chemical consumption, more efficient recovery of materials. Intuitively, I kind of lead to that conclusion, but it's not something definitive that I can really make a statement on.
So, kind of as you guys progress here, what do you see as the biggest hurdles kind of for your company coming up in the next 1 to 2 years?
Well, that's the exciting part. It's about being in a growing company, right? And then growing into from just a lab scale to where we are now in the demonstration plant. If you ask me what would some of the hurdles be at the lab scale, maybe there's some things you don't even foresee, or maybe there's some learnings that come about. But those unknown unknowns is what always so exciting for some engineers like myself. This demonstration plan is the reason we do these things. The scale up of these processes. Anybody, you'd be crazy to think if you're going from a lab scale to a multi-$100-million plant without testing everything and making sure, yes, your chemistry works out, but now how do those things scale in terms of engineering, from piping to mixing of these materials? How does it all flow? What is the ideal flow, right? So these are the things we're determining on a demonstration plant level, not with $100 million price tag, but something at a manageable size, where we can now collect this data and then scale more confidently. So I think those things will come. I think it's always expected for any development project, and I think that's going to be the exciting part. And so it's those unknown unknowns. Hate to say it sometimes. That's those. Sure. You won't know the hurdle until you get there, if you get there. And then I guess from a business side of things is, just for us making sure, especially in these markets and economic times, it's making sure we stay committed to the project we set out to do, keeping our team lean, making sure we commit a long runway and this work, because building strategic partnerships and planning for a commercial plant, this is kind of back and forth work that needs to happen with collaborators. We've done work with different collaborators on lab scale, pilot work, now demonstration plant work, and these discussions as well can take time, and to determine that path forward. And I think that's from a business end, some of those hurdles that can come up as well, and kind of where this market goes, right? How the EV adoption, what cells will be produced, what chemistries will be adopted the most. I think those are all those things we need to track on a daily basis, and I guess that's what makes it also exciting.
Thanks for all that. Do you have any? I'll give you last closing thoughts or anything that you like to we haven't hit on.
No, I mean, I just think, in general, thinking long term, if the world is going to make a transition to electrify everything, I see, we will need the mining of materials. We will need, maybe there is even some options for secondary use of batteries. But at the end of the day, I also see recycling as inevitable. Just as there are many EV companies and battery companies, I think there'll be multiple recycling companies in different geographic regions, and we'll constantly be challenging each other from whether a business perspective or technological perspective to do the most have the most efficient solution. And I think that's what we need to look at. We can't cut corners. We need to look at the most efficient solutions, and we need to, as an industry as a whole, push towards adopting the most efficient solutions. And to do that, we need these validation points, whether it's from third-party LCA reviews, from patents, publications, the peer review from experts, and we really need to put a lot of weight on those things as validation.
Well, Zarko, thanks so much for spending some time running me through all those details. I know I learned a lot more and really appreciate that deep dive there.
Thanks, Scott.
Yeah, and thanks everyone for joining us on Recycled EV Content, where we demystify the complex world of battery recycling, breaking down the technical so you don't have to. I know this time we went into greater detail than most, but if you still have any questions, please feel free to drop a comment below and I'll do my best to answer them. Thanks for watching, and bye for now.